All right, a couple more seconds. I think we have almost everyone. Yeah. Refresh. You can see the question. During the next question, I'll come around and figure it out. I see people do it all the time in class, so it must be doable. All right, so let's go through these one at a time. I'm going to go ahead and close this out. All right, if we take a sample, I want you guys, with all these questions, I want you picturing it. Even if it's a heavily calculation-based question, I want you visualizing the molecules within the container or whatever the system is. We're looking at the molecular level. So we're talking about an ideal gas, and we'll kind of come back a little bit to what that means. It's inside a steel container. What does that mean if it's inside a steel container?
That container does not expand or contract. So
that's an assumption we're going to make, that that steel container is a fixed volume. So that means that if we're thinking about P equals nRT, the calculation side of things, that means the volume is fixed. All right, it is heated up from 25 to 100 degrees Celsius. What does that mean about the average kinetic energy per particle? Josh?
It means that the speed increases. Sorry, I lost my voice.
Oh, no worries. That's how I'm calling you. Good idea to do the thumbs up. Right, so the average particle is going to be going faster. Does that mean that all the particles are going the same speed? So we want to be thinking about the particles. Remember the pool ball analogy we talked about in last class? That we have particles that are moving all around. These gases are bouncing around. There's an average speed that's going to increase when we warm things up. So that's kinetic energy, speed. Those two are synonymous with each other. Are they going to be colliding with each other more frequently? Why or why not, Manu?
Because the average speed is increasing. It means they're going to collide more frequently as well.
Fantastic. All right, so if we're visualizing the molecules, this is a really easy question to answer. What about the density? Is the density going to change?
no.
Can I have another voice? Let's hear from different people throughout the class today. Who wants to raise their hand and share why you think the density doesn't change? Matt.
Because there is a set amount of mass inside of the container. So the mass doesn't change and the volume doesn't change. Since density equals mass over volume.
Fantastic. All right. Once we break it down to the smaller parts, this is a really easy question as well. The density. How do we know that the mass doesn't change? Where does the mass come from in this problem? The mass is in the sample. The sample has atoms. The atoms have nuclei with protons and neutrons. So the number of protons and neutrons inside of this container does not change because it is a closed container. It's a closed system. We're not losing any mass. The volume doesn't change because we know that that's sealed, steel container. So then that ratio shouldn't change at all either. So then what about the pressure? Love?
That's how many particles hit, the frequency of particles being inside of the container. And that'd be the same as, say, collision frequency.
Great, so going back to what Manu said, because the particles are moving faster, they're going to be colliding more frequently with each other and with the outside of the container. All right, so the only one of these that does not change is based on the number of particles that there are in that container. Would this be true if we kept it at the same temperature and instead added more particles to that container? If we're adding more particles, we're adding more nucleons, we're adding more mass, which means that that density would now be different of that container. All right, so all these questions, remember, just go back to thinking about the molecular view of these. So we're still talking about this visualization of gas molecules specifically. Still describing everything on the molecular terminology and where gas is going to flow. This is still kind of what we're getting at. So we ended just before this last class. We're talking about now a sample of nitrogen gas. So there are all these N2 molecules. We have them at 3 different temperatures. and we've graphed molecular speed against the number of particles for each one of those three different scenarios at different temperatures. You have this also on your page, and that's question number 2. Go ahead and talk to your neighbor and try to figure out which one of these represents the coldest of those three samples. Couple more seconds.
Oh, yeah, that's right.
All right. Can I hear about your discussion? Can I hear from Kiana? What did you guys discuss? Which one of these do you think might be the coldest sample of nitrogen? We had these three samples, and why? Okay, so molecules are warmer, they move faster, so why would that mean that C is the answer? What's this question asking for again? So are you using that to say that, did you switch the axes maybe? So this is the number of them and this is the speed. Could we have someone else help out? Sarah?
When molecules get colder, they slow down.
Okay, great. So when molecules get colder, they slow down. The exact this is the same thing that Kiana said. You said they're warmer, they move faster. So then which one would you choose based off of, we're thinking about the coldest one?
A.
Why?
Because the molecular speed is lower than C.
Okay, and how do we describe, maybe even a little more detail, the molecular speed of A is slower? Let's be a little bit more detailed in the way we describe that. How can we do that?
When A has the same number of molecules as C, the speed is less than
What speed?
the speed of molecular speed of molecules.
So, which speed are we talking about? Are we talking about this speed? Are we talking about this speed? Are we talking about this speed? You know what I'm getting at? What did we just say for the last problem? Say again? The average speed is lower. Because if we look at sample A, so I completely agree. Sample A is the one that's colder. And sample A, if we pick a speed, pick any speed, right? 500. What is this? Meters per second. Okay? If we have a sample of gas, what percentage of A's molecules are moving this speed or faster?
Not very many.
5%, maybe less than 5%. What about for C? What percentage of them are moving that speed or faster?
60, 70?
Maybe 60%? Yeah, something like that. A lot higher percentage of them. So if I've done this in the past where I've asked students to draw me this graph before I give it to them of a cold and a warm sample. And what a lot of students would do first time around is they would draw this graph and they would draw one sample of gas and another sample of gas. And so this is what I just want to be more specific about. That it's not that all the gas particles are moving at the same speed and that this one is warmer than this one because they are moving faster. It's that the average particle has more kinetic energy and is moving faster. You see the distinction between those two? To me, it's a very important distinction that we're talking about the average speed of that sample is going to be higher than the individual ones. Are there more? I heard a couple people too saying that there's more molecules in one of these samples than the other. Why is that not true?
Distribution between the speeds.
So here at sample A, we have a lot more molecules moving very similar speed because they're cold. As we warm it up, that distribution gets bigger, so the amount at each speed is going to be less. If we were to try to figure out how many particles each had, we'd be looking at the area under the curve. We don't need to get into that as far as the technical detail, but all three of these samples would have the same number of particles. That's what this particular diagram shows. They're just spread out over more speed. The warm one has a lot of molecules at very many different speeds. The cold one has many fewer speeds that those molecules are at, so there's many more at each one of those speeds. All right, let's look at the next one then. So this one was all nitrogen gas. We looked at 3 different temperatures. Now I want to say, well, if those 3 are all different molecules now, we have another set of 3 samples. And those 3 samples are either chlorine gas, helium gas, or nitrogen gas, all at the same temperature, at room temperature, 300 degrees Kelvin. I want you to figure out which one of those samples would be C. Is it chlorine? Is it helium? Is it nitrogen? Go ahead and talk to your neighbor. See how we'd figure this out in this new scenario where those are 3 different samples, all at the same temperature. Okay, we don't have all the answers clicked in yet. Make sure to click in your answer. All right, we have a 2-to-1 split. Try to find someone around you that had a different answer. See why. See if you think they're right or if you can convince them you're right.
I agree.
If you agree, find someone else that didn't agree with you.
How'd it go? What did you guys say?
Couple more seconds.
It's going to be A or B. I don't remember reason for
All right, we're teetering. We're at a 5-to-1 ratio now. Can I have a new voice volunteer to explain which answer you chose and why? Which one of these 3 compounds would make most sense to be C? Joey?
I don't think wild guess. So is it B, helium?
What's your rationale for your wild guess?
Well, because the other two are more dense, so they're gonna hit each other more than they're gonna hit the wall. So you have less numbers there, you're gonna heat it up, and they're gonna be able to hit the wall more, so there'll be more pressure.
So I like where you're going. I like the molecular perspective that you have in thinking about hitting the wall. There's a couple different ways we can end up with. So you're thinking about pressure, maybe a little bit more so.
So you're gonna have more speed because they're not gonna helium. You have less. It's less dense, so they're gonna have more room to move around.
Okay, we're on the right track. Can someone else add to that? Someone add to that thought process. What's another reason we might say that helium would be the one that has the biggest distribution of speeds? Eric?
They have the same average kinetic energy, all of them, because they're at the same temperature. So since the other two gases are heavier, they have to be moving slower to have the same average kinetic energy.
Which is related to the density, right? The ones that are heavier have more density. And if we're thinking about if you think about having a basketball and having a little gumball, if we say that both of those have the same kinetic energy, that means that we're pushing them across the room with the same amount of energy. Which one is likely to be moving faster? Why?
Because it has less mass.
So if you give the same amount of force to two things, and one weighs a lot more than the other, the one that's heavier is going to be moving slower on average. The one that's lighter is going to be moving quicker. So that does relate to density. It does relate to collisions with the side of the wall. Let me ask one more question then along these lines. So this one is absolutely helium, is C. So then that means that A by default is the heaviest one of the three, so that's chlorine, Cl2. Which one of these All right, I'm going to open the clicker in 1 second. I can't open it with this written on there. Which one of these three samples do you think will have the highest pressure? The sample of chlorine, nitrogen, helium at the same temperature, or are all three going to have the same pressure? Go ahead and talk to your neighbor. Try to figure out which one of these you think is going to have the highest pressure, and I'll open the clickers in 1 second. All right, clickers are open. All right, we're split almost right down the middle. So let's talk it through. Can I get someone who says that A is going to have the highest pressure, and why? Moab?
Alright, so the formula PV equals to nRT. So volume is kept constant, the gas constant is constant, and then the temperature is constant. So the only thing that changes is N.
But all these have the same number of molecules.
You're right. I don't think it's
Okay. So why might someone choose A, or why might someone choose C? Either one of those. We have a decent number of people on both of those answers. Great. The logic is awesome there. They're moving faster, they're hitting the side of the container, that's how we measure pressure, they're going to have a higher pressure. So what's the little caveat that we have to add to that that leads us to the answer D?
It's the fact that they are all at the same temperature, and temperature is what affects the average speed.
Okay, so the reason that they all have different speeds is even though they have the same kinetic energy, they weigh a different amount. So if we go back to the idea of the gumball, right? If I throw the gumball and the basketball across the room and I give them both the same amount of energy, if you have a pressure sensor where they collide, which one is going to feel a higher force?
Neither. You gave them the same amount of energy.
They have the same amount of energy coming in. While this one has a much higher average speed, they don't weigh as much. So every collision is going to have a much smaller amount of force. These ones are moving much slower, but they are much heavier. So that means they are going to have the same amount of force with the whole population overall. Which is why, going back to what Mohit pointed out very beautifully when we started this discussion, in the equation for PV equals nRT, nowhere is there speed. There's temperature. So the temperature is really what impacts the force on the outside of the container, which influences if they're lighter, they're going to be moving faster on average. If they're heavier, they're going to be moving slower. Questions? So my answer to that would be all are moving at the same speed. Someone asked, is there an equation? PV equals nRT doesn't tell us anything about speed, so if we wanted to talk about speed, we could. We can use the root mean square equation, which has the molar mass. This is a symbol for molar mass you sometimes see in chemistry. Gas constant, temperature, and it's the square root of that relationship. Basically what I want you to take away from this is that the larger the molar mass is, the lower the speed is going to be. So this is the speed, the root mean square speed. Right? Don't calculate it. Don't worry about the equation. If you use the logic that we just did, you have as much information as I want from this equation. So that discussion that we just had, that's called kinetic molecular theory. It's talking about the amount of energy that particles have is related to their speed, and the force that they hit inside the container is related to their mass. And going back to ideal gases, there's a couple of assumptions that we make about ideal gases that don't necessarily apply at either really high temperatures or really high pressure. And that's this idea that all gas particles have elastic collisions.
Perfectly elastic collisions.
Which means they don't lose any energy when they collide with something else. That all the energy they had going into the side of the container is then maintained coming off. Okay, it works okay at atmospheric pressure and around room temperature. Once you get too far in the extremes, it doesn't work. We also kind of assume that gases don't have any volume, the molecules themselves, compared to the space that they have to go around in. This is kind of crazy.
Not true at very high pressures, but
a lot of different times. So if you think about clouds, we have a lot of water vapor, right? That means water molecules that are floating around in the air, but we slow them down enough, and when they get close to each other, then they have that attractive force, and now they're actually attracted to each other. They become a liquid. So they don't act as ideal gases in certain situations. And that's kind of the other assumption, is that molecules don't attract or repel each other, that there's no intermolecular forces when they're gas particles. Well, that stops being true when we either bring them really close together, increasing the pressure, or when we cool them down so they slow down, so when they do run into each other, now they're slow enough so they get a little bit of attraction to each other. So there's, on the back side of your worksheet, I think there are three questions? Three questions?
Two.
Those are some practice questions, so you can use the gas law stuff you did over the weekend or your homework, and use that to think about how do we calculate molar mass, and how do we determine empirical formula. Things that you already have been able to do, now we're just throwing one more additional way to do it into the mix. So if you're given gas information, then you can go ahead and figure out the identity of a molecule. So I'd highly advise practicing those, and that's something that we can pick up in office hours. You can put on Blackboard discussions. I made new Blackboard discussions that are post-exam 3, so that you don't have to go look through that long list. I find it not very organized by date or topic. It's kind of annoying. So now there's new discussion topics for logistics and for content past exam 3. So if you want to talk about these questions, that would be a great place to post. Put a picture up, talk through how you did it. Say, I'm stuck here. I don't know if this is the right answer. However you want to work through that. All right, so now we're going to shift gears and think about the application of weather patterns. Did anyone get a chance to go to this website, by the way? Super cool. Like, if there's a hurricane that's hitting the planet at any point in time, you literally can see the wind patterns, how that affects the wind everywhere else. You can do wind speed, you can do temperature, you can do a whole bunch of other things. So let's start thinking about, let's transport ourselves out of class. Let's go to Sunny Beach, Florida. Let's go to Mississippi. Do they have any beaches?
Yeah, they do. They do, actually.
All right, we're going to stand on the edge of the water, edge of the Gulf of Mexico. We're going to have our feet in the water, and we're going to be thinking about gas laws. Sounds like what you want to do, right?
Yeah, think about gas loss on vacation.
So we're going to think about the gases. I hope you do after this class. I hope the next time you go to the beach, you're like, I get it. All right, so let's think about the density of the air in the middle of the afternoon. Go ahead and talk to your neighbor. Try to figure out what I'm getting at here. All right, you guys are 50-50. Try to figure out how to justify one of these two answers. And let's add some specifics into this. Typically, if you're at the beach in the middle of the afternoon, what's warmer, the beach or the water? Okay, so let's keep that in mind. The beach is going to be warmer than the water. So how does that influence our decision of which of two bodies of air is more dense? Give you 30 more seconds to discuss this. All right. If we're on the beach and the sand is warmer than the water, is the air above the two inside of a steel container?
No.
So what does that mean?
They can flow.
It means that the air can expand, and those molecules can move further apart, or they can move closer together. Where do you think the air is going to expand or move further apart? Over the warm sand or over the cold water? They're going to expand over the warm sand. If the molecules of gas expand over the warm part of this scenario we're talking about, does that increase their density or decrease their density? Going back to Matt's definition of density, which is the mass over the volume. The mass is now spread out further apart. Did that increase our mass or decrease our mass for a given area right over the sand? It's going to decrease our mass. So if we think about the air over the beach, we're going to have density equals mass over volume. We're going to have a lower mass in any one given cube we're looking at, any volume we're looking at over the beach. That air expands, it goes elsewhere, right? It goes over the water, it goes further inland, it goes up. But now we have less mass there. So that means that the air over the land is less dense. Trip, do you have a question? So if those particles are moving faster, they're given more kinetic energy, then they're going to bounce off each other and expand and move further away from each other. So that means that we started with a lot of gas molecules in a certain volume. Now they're moving faster so that warmer air expands. And now we don't have as many gas particles in the same space. Joey?
So what about water evaporating going into the...
So water can be some of those gas particles.
Would that have anything to do with it being over the water and evaporating, putting more molecules into the air, which means they have more mass?
I don't know that that would change the density of molecules.
But if we put more mass over...
True, but that mass would probably be accounted for by an expansion of the ones that are currently there. I'm not sure. It might have a role, definitely. All right, so then let's take that answer and use that. We have a meeting point, right? We're standing right at it between the water and the land. We have two... Couple more seconds and click in your answers. All right, Anthony, can I hear your group's discussion?
We were just talking about how the air over the water is more dense compared to the air over the land, and the more dense would go under, so the air over the land would go above.
What do you guys think about that? That aligns with what the clickers have said for the most part. So you guys have said overall that the air over the land that is warmer, that is less dense, is going to rise. The more dense air is going to slide in and kind of take its place. So then let's take that and make a final statement about that. Which direction is the air going to flow if you're standing at the shore in the mid-afternoon on a warm day? Go ahead and click in your thoughts on this. You can talk to your neighbors first if you need to. Let's try to do 30, 45 seconds for this. Savannah, are you willing to share your group's discussion?
I originally said that the higher density air would move to, whereas lower density to just moving from concentration-wise. And then we also just said, like, logically, whenever you're standing on a shore, you normally feel a breeze hitting you.
You ever think about gas laws when you were experiencing that?
No.
Yeah, in chemistry when you go to the beach. All right, so exactly true. If we're standing at the edge of the water, the reason why we feel a sea breeze, the term sea breeze is exactly referring to that, is because we have high density air over the water because it's colder. Those molecules are packed closer together. Over the land, we have heat that expands that gas, that allows that gas to rise, and the colder air pushes in underneath it. But then we kind of end up with there's missing air out here, right? This air moved in, so what happened to the air that was here? Pulls it down from above, certain distance out. It depends on what beach we're at and how big the difference is in pressures there. Pulls that air down, which means that the air that rose in the beginning cools down as it goes up and gets pulled out. So you end up with this kind of vortex, this cycle that happens over a beach. all due to expansion and contraction of air. Going back to one of the things that Joey was talking about, well, this air has a lot more water molecules in it. So as that more moist air goes in over the land, it heats up, and then what happens to it? It expands, goes up, it cools down. What happens to cool air with lots of water molecules in it? It goes back this way, but what happens to the water molecules? They can form little clouds. They come back together, they form some precipitation sometimes, or little itty bitty clouds that float out, that then become part of the cycle again. And I have a little animation that kind of shows this at different times of the day. So what does that mean for earlier in the day? Or at night? At night, maybe the beach is colder than the Gulf, because the Gulf gets pretty warm. Let's see if I can... I hate how small this thing is. So let's take a look. Right now it's at noon at a beach. We have the air over the land is much warmer. It's going up. It's doing that cycle we talked about. I want you to watch as the sun sets what happens to the directionality of the breeze. What is that? So why is it that the breeze goes out in the middle of the night? Talk to your neighbor for 1 second. All right, can I hear from a new voice? Why is it that the breeze blows out towards the sea in the middle of the night? Can I get someone to take a stab at explaining it while we're watching this one more time?
It's moving back from...
Go ahead, Savannah.
It's moving back from the higher concentration to the land.
So concentration might not be the term I use.
Okay.
What would be another term that could work in that place? Trey, you want to say in a sentence?
The temperature is lower than it is in the ocean, so the density would change with the air above the beach.
So density or pressure, either one of those would have been fine to use in that place. So wherever we have the higher density, which is also higher pressure, we're going to end up with that pushing inward. And then that is going to raise up. But in the middle of the night, we have colder sand than we do water, because that water has absorbed heat all day and it holds on to it better. So that means that we're going to push the air out from the more dense to the less dense. So when you look at the weather maps on the Weather Channel or on your news channel, and you see there's an area of high pressure coming across the country. High pressure typically is how they describe high density. And so there's a little bit of nuance there that goes on, because thinking about pressure versus temperature, and there's a whole bunch of things, but I think if you think about density, this kind of system makes a lot of sense. All right, that is what I want you to be able to think through with gas laws. There's also a couple other components that have to do with pressures and doing some calculations. I think for the last couple of minutes in class, we have 9 minutes left in class. I think we're going to move past gas laws, and we're going to start talking about energetics of reaction. So go ahead and grab the other packet. It says activity number 34 in the front. You're welcome to do the first 2 pages on your own. We're going to start on Model 2, which is the 3rd page. If anyone doesn't have one, I think there's a couple extra copies in the back. So go ahead and work in pairs or groups of 3. start on Model 2. Go ahead and read the text, and then we're going to answer those questions towards the bottom. So in a couple minutes, we'll talk through critical thinking questions 5 and 6. And as Bria points out, please make sure you read the text to answer the questions. Alright, I want to hear, we're talking about the chemical reaction shown in figure 1. We have two hydrogen molecules, two hydrogen atoms. They're either as a molecule together or they're separate on either side of the equation. So do we think that that is an endothermic or an exothermic? And I want you to support your answer with specific statements above in the text. Logan, you good with that?
So it's endothermic because in the text it says that in order to break bonds, you have to take in energy.
In order to break bonds, we have to take in energy. It requires an input of energy. And so why does that make it endothermic?
Because it says if energy, in the first sentence says when a chemical process occurs, energy is either released in an exothermic process or absorbed. And so the breaking of bonds requires energy to pull the apart. So
Great.
Take in and then use input.
Fantastic. So if it requires energy, remember thinking about, I think the best example is those magnetic model kits that you may or may not have used in your lab, but you've seen me use a lot in class. That those are together because they are more stable together. Why are they more stable together? Two hydrogen atoms.
Because each hydrogen atom has one proton, one electron, and they want to get to two complete their...
They need a duet, right? They're in search for a way to have a noble gas electron configuration or mimic that. So they are more stable fulfilling that valence electrons with another electron. We're going back to quantum every time with our description of why. So that is an endothermic reaction. It requires energy to take them from more stable to less stable. All right, so then what about number 2? Gail, is the delta H for the chemical equation in figure 1 positive or negative?
Positive.
Is that a 50-50 guess? You didn't look very confident in your answer. Can I have someone...
Endothermic kinetic energy is positive.
Okay, so they are gaining energy.
So it takes a positive sign because gaining is represented with the positive. No? Exo means that you're taking it out, but it's negative.
So if we're talking about the system, if we are breaking a bond, you guys agree with that? That in order to pull them apart, the energy is going into the system, the energy of that system, delta H is going to be positive. Okay, I agree. What about question number 3? What would the chemical reaction be, which would have the same value of delta H, but with the opposite magnitude? Savannah?
It would be H plus H yields H2.
Great. And then we would have a negative delta H. Those two atoms would be becoming more stable. They are releasing energy to the surroundings. And that ends up being the same magnitude because it's the exact opposite reaction. All right, where are we at time-wise? We are just about out of time. You must bring this to class on Wednesday. We're going to spend a lot of time with this packet on Wednesday. So please make sure to bring this. I will be posting a pre-class quiz that's related to this material. I'll do that in the next hour or so you'll be able to do that for Wednesday's class. Exam wrapper is due Wednesday at the start of class. If you have any questions, I have office hours today, 3 to 4:30. Tomorrow from 1 to 2 p.m., I believe, whatever's on my calendar. And in between, I'm out. Stop by.